Okay, welcome back to 980. This is section 2.6, the section on functions. The very first thing that we would talk about here is, before we talk about functions, we would talk about a relation. A relation, a mathematical relation, is essentially a list of ordered pairs where one input leads to an output, right? Or a number of them, right? So in this case, I have a relation listed on the board. If the input is 1, the output is 2. The input is 2, the output is 5. Input of 3, output of 6. Input of 7, output of -2. They're just ordered pairs. And it might be discrete, like this, a certain number of them, or it might be continuous, like functions that we'll get to a little bit later. But that's essentially it, is just a set of ordered pairs. Right. The first entry of an ordered pair is always the input, whereas the second one is called the output, right? And so in this relation there is something called the domain. And that domain is the set of input values, essentially. Right. So the domain here is a set of numbers itself, but it's all of the input values. So 1, 2, 3, and 7 in this case. It's those. That's my domain. Those are all of the values for which, if I input these numbers, I can get an output defined by this function, or this relation. Right? On the other side of this is called the range. And the range is the set of outputs. Or the set of output values for the relation. Right? So in this case, that range is 2, 5, 6, and -2. So I'll write them in ascending order, so -2, and then 2, and then 5, and 6. Usually you'll see them in increasing order like this, right? But that's my domain, that's the range of this relation, right? These relations can be all sorts of things. They don't even have to be numbers, right? They could be cities with population, right? The input might be New York City. If your relation is population, I don't know, I'm going to make up a number. Let's call it 5 million people. It's probably wrong, but New York, 5 million, that's the relation. San Francisco, 3 million. Again, I'm pulling these numbers out of nowhere, so they're probably wrong. Don't fact check me on this. Salt Lake City, I don't know, 2 million, right? Whatever. But that's the relationship, is the city is the input, where the population of that city would be the output. But function is a little bit more strong than a relation, right? A function is a relation, but it's a relation where every input value is uniquely tied to an output value, right? For example, I have this relation here. Let's say we had New York City, and I don't know what that was, but 5 million people. Let's just pretend. Let's pretend I'm right for now, knowing that I'm probably not. And let's say we had San Francisco, and let's say there's 3 million people there, and Salt Lake City, and whatever it is, I don't know, 1 million. I don't know these numbers, I don't care. But each of these inputs only has one output, right? New York City has 5 million people. There's not two outputs for the single input. San Francisco has a single answer, 3 million. Salt Lake City, 1 million, right? Whereas, let's say, let's call this population, let's go with phone numbers, right? Let's say me, I'm an input, Scott. Well, I have a cell phone number. I'm not gonna write it here because you guys don't need to text me at 2 in the morning. But Scott has a cell phone. Nobody has this anymore because it's freaking not 1980, but let's say I had a home phone number, right? I have a home phone number. Let's say I have an office number. I in fact do, I have 2 of them. I don't know what either of them are, but I have 2 of them. I have a SLIC phone number, SLCC, and I have a phone number at UNLV. Right? This is very much not a function because you say, hey, what's the phone number for Scott? Which one? You know, right? You have to distinguish between which Scott that you want, right? And they're not different Scotts, it's all me, boom. It's my cell number, it's my, this one doesn't exist, whatever. But it's my SLIC office number, it's my UNLV number, my fax number, whatever. If you don't know the output given that input, now it's not a function because this input does not have a unique output, right? Whereas these ones do. New York City, 5 million. San Francisco, 3 million. There's an answer. What's the population of New York City? I don't have to say, oh, what answer do you want? But no, there's only one answer. It's 5 million. It's probably not, again, we're not worried about that, right? So the population is a function. This phone number list is not a function because there's 3, 4, 5 possible outputs for the same input, right? So let's look at a couple of relations and decide if they're functions or not. Let's say I have this relation that ties 1 to 2, 2 to 5, 5 to 2, 3 to 5, and 4 to 5. The question is this a function? And the answer is yes, because the output for 1 is unique, it's 2. The output for 2, there's only one answer, it's 5. The output for 5 is 2, the output for 3 is 5, the output is 4 for 4 is 5. The fact that I have 3 inputs that go to the same output doesn't matter. What matters is for every single input I have, there's only one output that I can get out of it. 1 only goes to one place. 2 only goes to one place. 3 goes to one place, 4 goes to one place, 5 goes to one place. Right? That makes this a function. Okay. This relation is not a function because 2 goes to 5 in one case, but it goes to 4 in another case. So that's like saying this guy's got 2 phone numbers, right? Which one do you want? I don't know, we have to figure it out. But because that input goes to 2 different outputs, 2 goes to 4, 2 goes to 5, it's not a function anymore. So this is not a function. This whole thing, not a function. All right. So, excuse me. Function notation, when we're talking about continuous functions, you know, a lot of times we see things like y equals, I don't know, 2x, right? And this is the relation notation. That there's some relationship between y and x, right? If x changes, y changes. If y changes, x changes. There's a relation there, right? This happens to be a function, though, because for everything that I put in for x, there's only going to be one answer. I can't plug in like 5 in here and say, well, it's 10 sometimes and something else some other time. No, it's 10 always, right? And that's the case for every number that I would put in here. And so we can write this in function notation as f of x, right? This is all one mathematical thing, it's just like it's a y. I can't separate the x from the f, it's just f of x. The function who has x as an input, right? And this is the exact same thing as this, except this is now in function notation. The nice thing about this function notation, though, is that I can evaluate things at certain places, and I can note it in my writing. So if I want to know what the value of this is at 5, I can write that the function evaluated at 5 is, and then I just replace the x with 5. The function evaluated at 5 is the expression where x has been replaced with the 5, and that's clearly 10. The function evaluated at 0 is that expression where x has been replaced with 0. And that is 0, right? And so I can do this all day long with all sorts of numbers. The function evaluated at 3 is that expression where x is changed into a 3, right? This is our function notation. It tells us if we're evaluating specifically at a number, it tells us what the number is that we're evaluating it at, and then we come down to an answer, right? So, if I'm interested in this function, let's back up to this function right here. I can be asked, what is the domain of this function? Well, the domain is any number that I can put into this function and have it give me a valid output, right? It's not discrete like we just dealt with, it's any number that I can put in there. And I can double any number. There's no number out there I can't double. And therefore the domain is everything. And so we always say that it's all real numbers. Because I can double anything. And then the range, we'll talk about range for a couple of these, but then range gets maybe a little bit more difficult, so we kind of back off of range for a little bit. You'll hit it again in pre-calc or calculus. But the range here is any number that is output. And I can reason through this that any number could be double another number, even say 5. 5 is double 2.5, right? And so every single number could be double a number, so I could possibly get every number out of this, and therefore the range is also all real numbers. Meaning I can put anything I want in there and get an output. And there's also any number that I want to get out, there is a number I can put in to get it. And that's why my range is everything, right? This isn't the case for everything. And again, our range kind of starts to get ugly a little bit, so we back away from talking about the range in a minute. But let's talk about domain for a couple of other functions. Let's say I have some function, and the function f, typically you would use f for function, but it doesn't have to be an f. F is just the name of the function. You could call it g. So let's say the function g of x, and a lot of times when you're dealing with 3 or 4 functions at the same time, you'll start calling them f of x, g of x, h of x to distinguish between the 3 of them. But let's say that I have the square root of x, right? And I want to figure out what the range is. Or not the range, sorry, the domain is what I'm interested in. What is the domain of this? Well, it's any number that I can put in for x and get a valid output. So any positive number I could put in, if I put in 4, the square root of that is 2. If I put in 9, the square root of that is 3. If I put in ugly numbers like maybe 5, the square root of 5 is something, but it's something, right? It's 2.1 something. I don't know what it is, but it's something, right? And so all of these positive numbers I can put in. I can put in 0, because the square root of 0 is 0. So anything that's positive is good, anything that's 0 is good, but if I try to throw a negative number in here, I start to get into trouble, right? I can't take the square root of a negative number and get a real number out of it, right? And so the domain here is 0 to infinity. All of those numbers are good. It's when I try to jump off to the left of 0 that things start to go awry. We'll talk about that. It actually comes into play. We're no longer in a real number system, but it'll happen. But for now, we're talking about the real number system, so we're talking about these numbers, 0 to infinity. They can be put into the absolute, or the square root function, right? The range here, again, we're going to stop caring about this, but the range is the same. Is also 0 to infinity, and I think you could argue that through, because the square root of 0 is 0, and as you start getting bigger numbers, you start getting bigger numbers out from the square root function, right? So that is the square root function, and of course we could get things a little bit hairier. Let's look at another function. Let's call it h, just for fun. Let's say we have h of x equals, and I have the square root of, let's go like say x plus 2. Right? Now I have to consider what's happening here. This x plus 2 could be at minimum 0, just like the square root of x, but I have an inequality that I have to solve, and that is this, that the x plus 2, the restriction here is that that is at least 0, but it could be more, right? But I can solve this inequality, subtract 2, and I get x is greater than or equal to negative 2. And any of those numbers will work, right? Including negative 2, because if I plug in negative 2, add 2 to it, it's 0. I can take the square root of 0, I'm fine there. So it's all of those numbers greater than or equal to negative 2. They could get uglier. Let's go f of x equals the square root of 2x minus 46. Right? It's the same idea though. Whatever's under the square root, this 2x minus 46, is simply limited in that it has to be at least 0. It's greater than or equal to 0, and I just solve this inequality. So I add 46. This gives me 2x has to be greater than or equal to 46, dividing side by 2, and my x value, right, because that's what I really care about here is what my x can be to make this work out. That simply has to be greater than or equal to 23. If I go less than that, 2x minus 46 will be less than 0, and I can't square root less than 0. So that's my domain here. All right. Excuse me. I have one other type of function that I have to be careful with as far as domain is concerned. Okay. So if I have, well, that's dumb. Sorry, I gave it away. I ruined it. Surprise! What happens when x is 0? That's where we're going with this, right? If x is 0, I'm trying to divide 3 by 0, and it doesn't work, right? So that's the other domain issue, is that you can't divide by 0. So here, we would simply say that the domain is x can't be 0. You can write it this way as a simple straight inequality, x cannot be equal to 0. Again, that really means all of the numbers between negative infinity and 0 union with the numbers from 0 to infinity, excluding that 0, right? But that's our things that we cannot divide by 0, so that the denominator can't be 0, and that denominator might be a little bit ugly sometimes. Such as, if I have, let's say, g of x equals 2 over x plus 5. Well, the idea is that my denominator can't be 0, and so I just simply start in and say my denominator can't be 0, and I create that strict cannot be inequality. And I can solve this just like an inequality that we've dealt with before. Minus 5 from both sides, right? And this gives me x cannot be negative 5, and I'm done. It can be anything but negative 5, which makes sense, because if x is negative 5, plus 5 is 0, I'm dividing by 0, and the world blows up, and I can't do it. If it's even a little bit uglier than that, let's say I have an h of x equals, let me just get rid of this, I'm going to run into it. Let's say I've got 1 over x squared plus 5x plus 6, right? Well, I can factor this denominator. This is the same thing as 1 over, the 6 could be a 2 and a 3, so I get x plus 2, x plus 3, right? And this whole denominator will be 0 if x plus 2 is 0, or if x plus 3 is 0, because these things are multiplied together. And so I get x plus 2 can't be 0, and I can also not have x plus 3 be 0, right? So I just subtract 2, x can't be negative 2, and subtract 3, and x cannot be negative 3. Those are my two conditions. It can be all real numbers except negative 2 and negative 3. And then the last little bit in this section talks about evaluating functions, and we talked about that a little bit in the beginning. Well, let's look at a couple more of those. Suppose I have some function f of x is equal to x squared minus 2x plus 1, right? Just a second degree polynomial. And I want to evaluate, let's say, f of 2 and f of negative 2. Okay? And you'll probably see this on an exam, you'll probably see this on the final exam because it's easy to mess this up, right? Let's do the 2 first. This one's easy. This is not where people get messed up a lot. But it is this expression, x squared minus 2x plus 1, except I've replaced my x with 2. And then I just evaluate, right? 2 squared is 4. 2 times 2 is also 4. And then I have plus 1, so 4 minus 4 is 0, plus 1 is 1. If I evaluate f of negative 2, this is where people mess up. I'm putting in negative 2 in for the x's, but this x is whatever number you put in needs to be squared, and since I'm putting in negative 2, it needs to be in parentheses and squared. Because I'm squaring negative 2, not just the 2, right? And that's the part where people mess up, is right here by not squaring negative 2, but leaving the negative outside and squaring the 2 instead. Minus 2 times that x is now negative 2 again, plus 1. So negative 2 squared is a positive 4. Minus 2 times minus 2 is plus 4 more. And then plus 1, this is 9. Right? So watch those. These are the killers. Right here, when you square a negative, make sure you get a positive out of that. All right. Thank you, and I will see you guys next time.